Right next door, a galaxy hides secrets that rewrite the rules of space. I am talking about the Triangulum Galaxy, a swirling cosmic pinwheel so close we can peer into its heart, and what we find there defies all expectation. This neighbor is not just another collection of stars, it is a treasure chest of cosmic oddities, each one a puzzle waiting to be solved. By the end of this journey, you will have explored 25 of the strangest objects ever found in another galaxy. We will encounter a black hole that should not exist, stars that vanish and reappear, and colossal structures that challenge everything we know about how the universe builds itself. What is the one cosmic mystery you find most compelling? Our first strange object is not an object at all, but a profound absence where we expected to find a monster. At the heart of most large galaxies, including our own Milky Way, lurks a supermassive black hole, a gravitational titan millions or even billions of times heavier than our Sun. These cosmic engines are often active, blazing with light as they devour matter. So when astronomers pointed their most powerful telescopes at the very center of the Triangulum Galaxy, they expected to find a similar beast. They found silence. The core of M33 is serene, almost suspiciously quiet. It lacks the brilliant, energetic outbursts that signal a feeding supermassive black hole. This presented a cosmic puzzle. Where is the monster in the middle? The search became intense. Scientists scrutinized the motions of stars swirling near the galactic center, looking for the telltale gravitational wobble that would betray a hidden giant. They listened for the faintest whispers of X-ray radiation, the signature of even a dormant black hole nibbling on stray gas. For decades, the results were inconclusive. The best estimates now suggest that if a supermassive black hole exists there, it is astonishingly small, perhaps only a few thousand times the mass of our Sun. In the grand scheme of galactic cores, that is a lightweight, a pebble compared to the mountain we anticipated. This leads to a fascinating theory. Perhaps the Triangulum Galaxy experienced a failed growth spurt. Maybe in its early history, it never merged with another large galaxy, an event that typically feeds and fattens the central black hole. Or perhaps its gas was so smoothly distributed that it never funneled enough material into the core to ignite a brilliant, active heart. This quiet center makes M33 a living fossil, a glimpse into what galaxies might look like if they avoid the violent mergers that create the giants we usually study. Its peaceful core challenges our assumptions, suggesting that the path to building a galaxy has many forks, and not all of them lead to a ravenous beast at the center. So the first great strangeness of the Triangulum Galaxy is what is not there, a missing monarch that forces us to rewrite the story of how galaxies grow up. But the quiet heart of the Triangulum Galaxy is more than made up for by the screaming beacons orbiting around it. One of those beacons is a cosmic paradox, an object so bright it should not be possible. Designated M33X7, this is an ultraluminous X-ray source, a ULX. To understand why this is so strange, you need to picture a stellar mass black hole, the kind formed when a giant star collapses. It might be 10 or 20 times the mass of our Sun. Such black holes have a theoretical speed limit for eating called the Eddington limit. Think of it like this: as matter falls in, it gets incredibly hot and blasts out radiation. That radiation pushes outward like a fierce wind. If the black hole eats too fast, that radiation wind becomes so powerful it actually blows away the incoming food, cutting off its own supply. It is a natural cosmic governor. Now, M33X7 ignores that governor completely. It is consuming material at such a ferocious rate that it shines with the X-ray brightness of millions of suns. It is one of the most luminous objects of its kind in our entire local universe. How can it break the rules? Astronomers have a leading suspect, a gluttonous feast enabled by a cosmic partner. The best explanation is that this black hole is locked in a tight, deadly dance with a truly massive companion star, a bloated giant pouring its very substance into the black hole's grasp. The stream of gas is so dense, so relentless, that it overwhelms the pushing force of the radiation, allowing the black hole to gorge itself beyond all expected limits. For years, confirming this meant finding that companion star, the optical counterpart hidden in the glare. It was a needle in a galactic haystack, but patient observations finally spotted it, a massive, hot star indeed orbiting the invisible X-ray monster. This confirmed the picture of a binary system, a cosmic vampire and its donor, yet the discovery only deepens the mystery. What kind of star can lose so much material so quickly without being completely torn apart? How did this extreme pairing even form? M33X7 is not just a bright spot on a map, it is a natural laboratory, testing the absolute extremes of black hole physics and stellar evolution right in our galactic backyard. Yet the Triangulum Galaxy's capacity for extremes does not end with invisible monsters. It also hosts a stellar nursery of such staggering size that it redefines the word colossal. This is NGC 604, a glowing cloud of gas and dust so immense it makes our galaxy's most famous nursery, the Orion Nebula, look like a mere spark by comparison. If you were to place the Orion Nebula inside NGC 604, it would be a small, faint patch lost in a sea of luminous gas. This is not just a bigger cloud, it is an entire stellar metropolis under construction. Within this vast expanse, the raw chaos of creation is on full display. NGC 604 is what astronomers call a giant H2 region, a cloud of hydrogen gas that has been ionized or stripped of its electrons by the blistering radiation of newborn stars. And what stars they are! Nestled inside this nebula are not dozens but thousands of young, hot stars. Among them are more than 200 stars that are truly monstrous, each one dozens of times more massive than our Sun and shining with a ferocious blue-white light. These are O-type stars, the rarest, hottest, and shortest-lived stars in the universe. In our entire Milky Way galaxy, we only know of a few dozen such titans. Here, in this one nebula in a neighboring galaxy, they are gathered in a single, spectacular cluster. The effect these stars have on their birthplace is both beautiful and violent. Their intense ultraviolet radiation floods the nebula, causing the gas to glow in those iconic reds and pinks we see in images. But they also blast out powerful stellar winds, streams of charged particles moving at millions of kilometers per hour. These winds act like cosmic sculptors, carving vast cavities and intricate pillars within the gas, and triggering new waves of star formation at the cloud's edges as they compress the material. You are witnessing the feedback loop of creation and destruction that governs how galaxies evolve. This makes NGC 604 more than a pretty picture. It is a natural laboratory, a rare chance to study star birth on an industrial scale. In our own galaxy, we see star-forming regions piece by piece, but here we have a panoramic view of the entire process happening all at once. Astronomers can study how these massive stars interact with each other, how their collective winds shape their environment, and what happens when so many stellar giants are born in the same place at the same time. It is like comparing a single family home to an entire city being built from the ground up. The scale of NGC 604 offers a fundamental question. Is this how all the great star clusters in the early universe were born? This nebula is a window into a more frantic, more productive era of cosmic history, happening right next door. The brilliance of those stellar giants is matched only by the profound mystery of a single, flickering point of light elsewhere in the galaxy. Among the billions of stars in the Triangulum, one stands out for its erratic and dramatic behavior, a variable star known only by a catalog number that belies its strangeness. This star undergoes changes so extreme they baffle astronomers, not just dimming and brightening, but shifting its apparent color in ways that defy simple classification. Studying a single star in another galaxy is an immense challenge. It is like trying to observe the flicker of a specific candle flame from miles away, while it sits in the middle of a sprawling, brilliantly lit city. The light from that one star must be painstakingly separated from the glow of its neighbors and the faint haze of the galaxy itself. Every measurement is a triumph of technology and patience. So what is this star doing? The leading hypothesis is that it is a red supergiant, a vast, cool, and unstable star in the final chapters of its life. Such stars are known to pulsate, swelling and shrinking rhythmically as their internal furnaces struggle for balance. But this star's variations are wilder, more extreme than typical pulsations. Its brightness can swing dramatically over months or years, and the associated color changes suggest its surface temperature is also fluctuating wildly. This has led to other, more dramatic ideas. Perhaps it is not just pulsating, but is in a phase of catastrophic eruption, violently expelling shells of its own atmosphere into space in fits and starts. Each eruption would temporarily shroud the star in a cloud of its own material, dimming and reddening its light before the cloud disperses. Another compelling theory involves not just the star, but its environment. Could this red giant be surrounded by a vast, clumpy disk of dust and debris, perhaps the remnants of a consumed companion star or a previous eruption? As the star itself changes brightness, its light would interact with this uneven disk in complex ways, filtering its color and intensity in a pattern we struggle to decode. Untangling this mystery requires a kind of cosmic endurance we rarely consider. Astronomers must monitor this star not for nights or months, but for decades, patiently recording its every flicker to build a light curve that spans a human lifetime. Only with that long-term record can they begin to see the true patterns, or the terrifying lack of them, in its behavior. This star is a reminder that even in an age of powerful telescopes, some cosmic puzzles are solved not in a flash of insight, but through the slow, dedicated accumulation of data, one faint photon at a time. While the erratic star may be dying in fits and starts, other stars in the Triangulum Galaxy have already met their end in spectacular, definitive explosions. Among the scattered debris of these supernovae, two remnants stand out not just for their violence, but for their peculiar, almost mirrored strangeness. In the radio and X-ray wavelengths that reveal the aftermath of stellar death, these objects do not look like the simple, expanding bubbles we often see. One appears as a distorted ring, a broken circle of glowing gas. The other resembles a clumpy shell with strange, protruding jets or lobes, as if the explosion was channeled in specific directions. Their unusual shapes are the first clue that we are not looking at ordinary stellar deaths. The most tantalizing theory to explain such odd, paired structures involves a cosmic tragedy of two stars. Imagine a binary system where both stars were massive, bound together in a tight orbit. The first star explodes as a supernova. For a time, its remnant expands into the space around the surviving companion. Then, millennia later, the second star also reaches the end of its life and detonates. The blast wave from this second supernova would then slam into the debris field left by the first, creating a chaotic, mixed-up structure. The shockwaves would collide, compress gas in uneven ways, and sculpt the remnant into those bizarre rings and twisted shells we observe. It is a cosmic echo, one explosion literally reshaping the ghost of its partner. Another possibility is that we are seeing the intricate handiwork of a single, extraordinarily messy star. Some massive stars shed immense amounts of material in violent winds long before they explode. This ejected gas forms a complex circumstellar environment, a dense cloud of the star's own former outer layers. When the supernova finally happens, the blast wave expands not into empty space, but into this pre-existing cloud. The collision can create ripples, cavities, and bright rings where the shock front plows into denser pockets of material. It is like setting off an explosion inside a labyrinth of its own making. The true story, however, is written in the chemical fingerprints of the gas. By analyzing the light from these remnants, astronomers can determine what elements are present and in what quantities. In a typical supernova remnant, we expect to find heavy elements forged in the star's core and during the explosion itself, like oxygen, neon, silicon, and iron. But in these strange remnants, the chemistry can be even more revealing. If they are from two different stars, the mix of elements might show two distinct signatures layered atop one another. If it is from a single star that shed layers in episodes, the chemistry might show different abundances in the ring versus the shell, a timeline of the star's pre-death eruptions written in atomic code. These twin remnants are more than cosmic wreckage. They are forensic sites, and their distorted shapes are the evidence of a dramatic stellar history, whether of a doomed partnership or a profoundly unstable solo act. But the story of stellar death is only one chapter in a much larger cycle, a cycle that begins in darkness. Within the brilliant tapestry of the Triangulum Galaxy, there exists a profound patch of nothing, a black silhouette against a sea of light. This is a dark globule, a dense, cold cloud of gas and dust so thick it completely blocks the starlight from a rich cluster behind it. From our vantage point, it looks like a hole punched in the galaxy, a perfect circle of emptiness. Yet this void is not empty at all, it is a cocoon. We know these objects in our own galaxy as Bok globules, named for the astronomer who studied them. They are the cold, dense nurseries where new stars are born, places where gravity slowly overcomes the pressure of the gas, causing the cloud to collapse inward on itself. But seeing one in such clarity in another galaxy is a rare gift. The scale of this particular globule is what makes it so strange. It is not a wispy filament, it is a sharply defined, almost perfectly circular blot of darkness. Its opacity tells us the dust within it is incredibly concentrated, a testament to the cold, quiet conditions that allowed it to form without being blown apart by radiation from nearby stars. This dark spot is more than a shadow, it is a scientific instrument. By analyzing the starlight from the bright cluster as it filters around the edges of the globule, astronomers can perform a kind of cosmic chemistry experiment. They can measure precisely how much light is extinguished at different colors. Blue light, with its shorter wavelengths, is scattered and absorbed more easily by tiny dust grains than red light. This process, called interstellar reddening, is the same reason our sun looks red at sunset, its light passing through more of Earth's dusty atmosphere. By quantifying this effect in the Triangulum Galaxy, scientists can determine the exact size, composition, and distribution of the dust grains in that distant cloud. They are learning the recipe for cosmic soot in another galaxy. Is it the same as the dust in our own Milky Way, or does it have a different blend of silicates, carbon, and ice? The answer helps us understand the universal processes that create the raw materials for planets and, ultimately, life itself. So this strange object, a defined patch of nothing, becomes a window into the microscopic building blocks of everything we see. It reminds us that creation often begins in the deepest darkness, and that sometimes, to understand the light, we must first study the shadow. That profound darkness of the stellar nursery is shattered by the violent passage of a cosmic bullet. Streaking across the face of the Triangulum Galaxy is a runaway star, a massive blue-white titan moving so fast it is essentially escaping the galaxy's gravitational grasp. This is not a star drifting peacefully with its neighbors. It is a projectile plowing through the delicate interstellar medium at a significant fraction of the speed of light. Its journey alone tells a story of incredible violence in its past. How does a star, an object millions of times more massive than our entire planet, get kicked to such extreme velocities? Astronomers have two primary theories, each a testament to the chaotic forces at play in dense stellar environments. The first scenario is a gravitational slingshot from a broken partnership. Imagine a binary star system, two massive stars orbiting one another. If one of them goes supernova, the explosion is not perfectly symmetrical. The sudden, catastrophic loss of mass can be like cutting a tether, violently flinging the surviving companion star away like a stone from a sling. The second possibility involves a stellar billiards game in the crowded core of a massive star cluster. In such dense environments, close gravitational encounters between stars are common. A star can swing too close to a binary pair, receiving a powerful gravitational boost that ejects it from the cluster entirely, sending it racing out into the galactic disk. This particular runaway star in M33 is not just a speeding point of light, it is actively announcing its presence through the chaos it leaves in its wake. As it hurtles through space, it rams into the thin gas that floats between the stars. Because the star is moving faster than the local speed of sound in that gas, it creates a shock wave, much like the sonic boom of a jet breaking the sound barrier. This forms a brilliant, arcing structure called a bow shock, a visible wave of compressed and heated gas that glows in infrared and sometimes visible light. It looks like a cosmic wave breaking ahead of a stellar ship. This bow shock is more than a spectacular light show, it is a scientific instrument. By studying its shape, size, and brightness, astronomers can measure the star's incredible speed and direction. They can also probe the properties of the invisible interstellar medium it is traveling through, gauging its density and composition. The runaway star becomes a natural probe, revealing conditions in parts of the galaxy we could never study otherwise. It leaves a temporary scar on the galaxy, a brilliant testament to the fact that even the seemingly fixed points of light in the night sky can be born from and create unimaginable turmoil. The violence of a runaway star carves a visible scar, but the Triangulum Galaxy hides even deeper secrets in wavelengths of light our eyes cannot see. One of its most perplexing objects is not a brilliant point of light at all, but a ghost, a source of immense energy that only reveals itself in the infrared. This strange object is a brilliant beacon in the thermal glow of heat radiation, yet it remains faint or even completely invisible in the optical light our eyes perceive. It is a cosmic contradiction, shouting its presence in one language while remaining silent in another. So what is this unidentified infrared object? The answer is not simple because its strange signature points to three very different, equally fascinating possibilities. The first is a stellar birth shrouded in utter darkness. It could be a deeply embedded protostar, a newborn sun still cocooned within the dense, cold cloud of gas and dust that formed it. At this earliest stage, the star's visible light is completely trapped by the surrounding material, but the heat from its gravitational collapse and first flickers of nuclear fusion warms the dust, causing it to glow brightly in the infrared. It is a star being born behind a thick cosmic curtain. The second possibility lies at the opposite end of a star's life. This could be a highly evolved star, like a red giant or an asymptotic giant branch star that has puffed off enormous amounts of its own atmosphere. This ejected material forms a vast, cool shell of dust around the star, a circumstellar envelope. The star itself might be faint and red in visible light, but its intense radiation heats this surrounding dust to temperatures that make it blaze in the infrared. It is a star writing its final chapter in a cloak of its own ashes. The third, and perhaps most dramatic, explanation is that this single infrared point is not one object, but an entire region of intense, hidden activity. It could be a compact cluster of newly formed massive stars, so deeply buried within a molecular cloud that their collective ultraviolet light is completely absorbed. That absorbed energy, however, does not vanish. It is converted into heat, making the entire dust cloud around them radiate fiercely in the infrared. This would be a stellar nursery operating in stealth mode, its brilliant young stars invisible, but their profound effect on their environment unmistakable. Unraveling this mystery is a task for specialized eyes. Ordinary optical telescopes saw nothing remarkable here, or at best, a faint smudge. It was the Spitzer Space Telescope, with its sensitive infrared instruments, that first identified this object as something extraordinary. Now, the James Webb Space Telescope, with its unprecedented resolution and sensitivity in the infrared, is the key to solving the puzzle. Webb can peer through the dust, analyzing the precise spectrum of the infrared light to detect the chemical fingerprints within. Does the spectrum show the simple heat of warm dust, or does it reveal the specific emission lines of complex molecules and ices that would point to a cold, star-forming cloud? Could it detect the subtle signature of a carbon-rich atmosphere from an old, dying star? Each possibility leaves a different mark in the light. This unidentified object is a perfect example of how much of the universe remains hidden from our ordinary sight. It challenges the very notion of what an object is, reminding us that in the cosmos, what you see is only a tiny fraction of what is actually there, and the greatest dramas often play out in the dark. The hidden heat of that infrared object reveals one phase of stellar death, but in another corner of the galaxy, we see the final, beautiful breath of a star painted across the void. This is a planetary nebula, a common enough cosmic object, but this one possesses a form that shatters all expectations. Instead of a simple, glowing sphere or even a symmetrical ring, this nebula exhibits a wild, asymmetric shape. It might appear as two opposing lobes, like an hourglass, or even a faint, twisted spiral, as if the dying star coughed out its atmosphere while spinning violently. Such intricate structure is a direct challenge to the old, quiet model of stellar demise. For a long time, astronomers pictured a lone, aging star gently puffing away its outer layers in a series of spherical waves, creating a bubble that would glow under the ultraviolet radiation from the exposed hot core. That model produces beautiful, often round nebulae, but this chaotic form tells a story of interference, of a death that was anything but gentle and solitary. The leading suspect in this cosmic sculpting is a companion star. Imagine a dying red giant star with a smaller, denser partner in a close orbit. As the giant swells and begins to shed its atmosphere, that material doesn't just float away evenly. The gravitational pull of the companion star funnels the outflow, shaping it into jets or confining it to a dense disk around the binary pair. The result is a bipolar nebula, with material ejected most strongly from the poles of the system, creating those distinct lobes or an hourglass figure. In the most dynamic cases, the orbital motion of the two stars can imprint a spiral pattern onto the expelled gas, a frozen record of their dance. Magnetic fields provide another compelling artist's tool. A strong, organized magnetic field emanating from the dying star's core can act like an invisible cage, channeling the ionized gas along its lines of force and preventing a uniform expansion. This can create complex, knotted structures within the nebula, defying simple geometry. But the true story of this star's life and death is written not just in its shape, but in its light. By dissecting the nebula's glow with a spectrograph, astronomers perform a kind of cosmic autopsy, reading the chemical abundance of the expelled material. This is the star's final testament. The spectrum reveals which elements were cooked up in its core and dredged to the surface during its final tumultuous phases. We might find unusually high amounts of carbon or nitrogen, signs of specific fusion processes. We could detect the fingerprints of rare elements like neon or argon, forged in the star's final moments or in the shockwaves of the ejection itself. This chemical analysis answers profound questions. Was this a star of moderate mass, like our Sun will one day become, or was it more massive? Did it undergo several distinct episodes of mass loss, each with a different chemical signature now layered in the nebula's shell? The peculiar shape and the unique chemistry are two chapters of the same story. The shape tells us about the dynamics of the death, the forces that guided the final expulsion. The chemistry tells us about the internal life of the star, the nuclear reactions that defined its existence. Together, they transform a pretty cosmic cloud into a detailed biography, a reminder that even in its end, a star does not fade quietly, but leaves behind a complex and revealing monument to its long, fiery life. That final monument to a star's life exists within a galaxy we think of as a single, isolated island. But the Triangulum Galaxy is not alone in the void. One of its strangest features is not within its spiral arms, but just beyond them, a small, misshapen smudge of light that tells a story of gravitational theft. This is a dwarf satellite galaxy, a tiny companion caught in M33's immense gravitational pull. It is not a neat, round sphere of stars like many dwarf galaxies. It appears distorted, stretched, as if it is being slowly pulled apart. This is the unmistakable signature of a galactic interaction, a minor merger in progress. The evidence is not just in the dwarf's twisted shape, but in the faint, ghostly bridges that may connect it to its larger host. Astronomers search for tidal streams, great arcs of stars and gas that have been stripped away from the smaller galaxy by tidal forces, much like the way the moon's gravity pulls on Earth's oceans. These streams are like cosmic breadcrumbs, tracing the path of the dwarf's orbit and its ongoing dissolution. They are faint and incredibly difficult to detect against the brilliant backdrop of M33 itself, requiring painstaking observations to separate their subtle light from the galaxy's main disk. This slow motion capture reveals a fundamental process of galactic growth. Large galaxies like our Milky Way did not form in isolation. They built themselves over billions of years by consuming smaller neighbors. The Triangulum Galaxy is doing the same right now on a modest scale. This interacting pair shows us that even a galaxy that appears beautifully intact and solitary is in fact a dynamic system, constantly reshaping its surroundings and digesting the cosmic building blocks around it. But the challenge of seeing clearly in this crowded neighborhood goes even deeper. When we gaze at a detailed image of the Triangulum Galaxy, we are not just looking at M33. We are looking through it, scattered across that field of view, hidden among its billions of stars and glowing nebulae, are countless background galaxies, each one an entire island universe billions of light years further away. They appear as tiny, fuzzy ovals or faint spirals, often mistaken for fuzzy star clusters or nebulae within M33 itself. Telling the difference is a fundamental puzzle in extragalactic astronomy. Is that small, faint smudge a globular cluster orbiting M33, or a giant elliptical galaxy 10 times more distant? The key often lies in the details of its light. A distant galaxy will have a more uniform, smooth glow, while a star cluster within M33 might be resolvable into individual pinprick stars with enough telescope power. Their colors are also a clue, affected by the redshift of the expanding universe and the composition of their stars. This creates a celestial illusion, a sense of profound depth. The Triangulum Galaxy becomes a foreground screen, and every confirmed background galaxy is a window punched through it, offering a glimpse into the far more distant universe. It is a reminder that our view of the cosmos is a layered masterpiece, where distinguishing what is close from what is unimaginably far away is the first, and often most difficult, step in mapping the true structure of everything. Our cosmic yardstick has a crack in its markings. Cepheid variable stars are among the most trusted tools in astronomy, the foundation upon which we measure the vast distances to other galaxies. Their magic lies in a beautifully simple relationship. The longer their pulsation period, the more intrinsically bright they are. By measuring how long it takes a cepheid to brighten and dim, we can calculate its true luminosity, compare that to how faint it appears from Earth, and thus determine its distance with remarkable precision. It is this very method that helped Edwin Hubble prove the universe is expanding. Yet in the Triangulum Galaxy, we find a Cepheid that refuses to follow the rules. Its pulsation period and its observed brightness are out of sync, creating a discrepancy that throws its distance measurement into question. This is not a minor calibration error, it is a fundamental anomaly that forces us to scrutinize our most reliable cosmic ruler. The first suspect is cosmic dust. Interstellar dust, like a fine fog, scatters and absorbs starlight, making stars appear dimmer and redder than they truly are. If this particular Cepheid is hiding behind an unexpected veil of dust within M33, our measurement of its apparent brightness would be too low. We would think it is farther away than it actually is. Correcting for this extinction is a constant challenge, requiring careful measurements of the star's color to estimate how much its light has been dimmed. But what if the dust correction is not the answer? Then we must look at the star itself. The period luminosity relationship was calibrated using Cepheids in our own galaxy. What if this star in M33 has a different chemical composition, a different metallicity? The abundance of elements heavier than hydrogen and helium can affect a star's internal structure and opacity, subtly changing how it pulsates and how bright it becomes. A Cepheid born from gas that is poorer in metals might pulsate with a slightly different rhythm for its given brightness, throwing off our cosmic calculations. This leads to an even more intriguing possibility. Perhaps this is not a classical Cepheid at all. The family of pulsating variable stars is diverse. There are type II Cepheids often found in old stellar populations and anomalous Cepheids which are brighter than expected for their period. Could this misfit star belong to one of these other classes, masquerading as a standard ruler? Identifying its true nature requires peeling back the layers of its light. Astronomers take a spectrum, dissecting its glow to determine its temperature, surface gravity, and most importantly, its chemical fingerprint. They also study its light curve with extreme precision, analyzing not just the period, but the exact shape of its brightening and dimming curve, which can be a telltale sign of its pulsation mode and class. The implications of this single anomalous star ripple far beyond its own location. If we cannot perfectly trust one Cepheid, we must question the calibration of all of them, especially in galaxies with different chemical histories than our own. This forces a refinement of the entire cosmic distance ladder. Each anomaly we find, each Cepheid that does not fit, is an opportunity to improve our models. We learn how to better account for dust, to incorporate metallicity effects into the period-luminosity relation, and to more carefully classify the stars we use as mileposts. This strange object, a flickering point of light that does not behave, is therefore one of the most valuable in the galaxy. It is not a broken tool, but a teacher, showing us the subtle complexities we must understand if we are to ever map the true scale of the cosmos. The cosmic yardstick may have a crack, but the sheer scale of some structures in M33 is beyond any doubt. In a galaxy brimming with stellar nurseries, one object stands apart not for its size, but for its staggering density and youth. This is the superstar cluster M33EC1, a single, brilliant point of light that is not a star, but a city of stars. Within a region of space not much larger than the distance between our Sun and its nearest stellar neighbors, this cluster packs hundreds of thousands of stars, all born together in a single, ferocious burst of creation. To find a comparison, you must look at the ancient globular clusters that orbit our Milky Way, those spherical swarms of hundreds of thousands of ancient stars. They share the same incredible stellar density, the same gravitational bond, but there the similarity ends. While globular clusters are fossils from the universe's infancy, over 10 billion years old, M33EC1 is a newborn. Its stars are brilliant, hot, and blue, blazing with the intensity of youth, likely only a few million years old. This presents a fascinating evolutionary puzzle. We are looking at an object that has the mass and structure of a future globular cluster, but it is being observed at the very moment of its birth. How does such a dense, massive cluster form all at once? The answer lies in conditions of extreme pressure. It requires a molecular cloud of exceptional mass and density, one that remains undisturbed long enough for gravity to trigger a collapse not in several pockets, but across its entire vast expanse. Instead of forming a scattered association of stars, the entire cloud fragments into a packed stellar metropolis in one coordinated, violent event. It is star formation pushed to its absolute limit. The core of this cluster, as seen in detailed images, is not a diffuse glow but a searing, almost solid-looking knot of light, a testament to the incredible number of stars crammed into that tiny volume. The gravitational pull in that core must be immense, a complex dance of thousands of suns in constant, close motion. This leads to the critical question of survival. Will M33EC1 live to see its 10 billionth birthday? The environment inside such a dense young cluster is brutally competitive. With so many massive stars born together, supernova explosions will begin to rock the cluster in just a few million years. These blasts can eject vast amounts of gas, stripping the cluster of the material that binds it together gravitationally. If enough mass is lost, the cluster could dissolve, its stars scattering into the galactic disk like a burst piñata. But if it retains enough of its stellar mass through this violent adolescence, its own gravity will hold it together. Over eons, dynamical friction will cause the most massive stars to sink to the center, while lighter stars migrate outward, gradually shaping it into the perfect sphere of an ancient globular cluster. This object is a time capsule in two directions. It shows us what the progenitors of today's oldest globular clusters might have looked like in their dazzling, chaotic youth. And it offers a prediction, a glimpse of what this brilliant point of light could become, a frozen relic of stellar fire that will outlast the galaxy's spiral arms themselves. While superstar clusters blaze with youth, other parts of the galaxy exist in a state of profound quiet. Drifting through the dark spaces between the spiral arms is a ghost, a vast, diffuse cloud of neutral hydrogen gas detected not by its light, but by the faint radio whispers of its atoms. This cloud is immense, potentially spanning thousands of light years, yet it holds a puzzling secret. Within its cold, tenuous expanse, there are no stars being born. It is a reservoir of potential that refuses to ignite, a cosmic blank canvas. How does such a large mass of raw material avoid the gravitational collapse that should, by all rights, be seeding it with new suns? The answer lies in its very nature. This is not the hot, ionized hydrogen of a glowing nebula, energized by nearby stellar radiation. This is neutral hydrogen, abbreviated HI by astronomers, where each atom's proton and electron remain peacefully bound together. It is cold, dark, and incredibly diffuse. The particles within it are so spread out that the cloud's own gravity is too weak to pull them together against their inherent motion and the gentle pressure of the surrounding space. It exists in a state of equilibrium, a sleepy giant lacking the trigger to wake up. So where did this isolated cloud come from? One possibility is that it is truly primordial, a leftover wisp of the pristine gas from which the galaxy itself formed billions of years ago. Somehow, this pocket avoided being swept up into the denser spiral arms or compressed by any passing shockwaves. It is a fossil, a living relic of the galaxy's raw, unprocessed building material. A more dynamic origin story involves galactic interactions. The cloud could be a tidal remnant, a strand of gas pulled out during a close encounter with a dwarf satellite galaxy, like the one we see being consumed. This gravitational tug of war can stretch and eject long streams of gas into the galactic halo, leaving them stranded far from the denser regions where star formation typically occurs. Another violent possibility is ram pressure stripping. As the Triangulum Galaxy moves through the thin, hot gas that fills the space between galaxies in its local group, this intergalactic medium acts like a cosmic wind. For a diffuse cloud, this wind can be strong enough to literally blow the gas away from the galaxy's disk, shearing it off and leaving it adrift in intergalactic space, too disrupted and diffused to ever coalesce. The future of this starless cloud is a slow, cosmic fade. Without a catalyst, a collision with another cloud, the shock wave from a distant supernova, or the gravitational nudge of a passing dark matter clump, it may simply remain in its dormant state for eons. Gradually, the faint ultraviolet radiation that permeates space, the extragalactic background light, may ionize it, stripping electrons from the atoms and causing it to fade from the radio signature we can detect. Alternatively, it could eventually drift back into the galaxy's disk over billions of years, finally merging with a spiral arm and perhaps one day far in the future, contributing to a new generation of stars. This invisible cloud is a crucial reminder. The visible galaxy of stars and nebulae is only a small part of the story. Most of a galaxy's ordinary matter exists in these cold, dark reservoirs, the unseen fuel for future epochs. By studying this strange, starless object, we are not just looking at emptiness, we are taking inventory of the galaxy's potential, mapping the dormant seeds of tomorrow's light. Deep within that silent reservoir of potential, a different kind of relationship plays out with violent and clockwork precision. Orbiting each other in a tight, lethal embrace is an X-ray binary system, a pairing of a dead stellar remnant and a living donor star. One member is a compact object, either a neutron star or a black hole, the dense corpse of a supernova. Its companion is a normal star, swollen and unfortunate. The immense gravity of the corpse relentlessly strips gas from the outer layers of the living star. This stolen material does not fall straight in, but spirals down, forming a searingly hot disk of plasma around the compact object. As this matter compresses and heats to millions of degrees, it screams out in X-rays, turning the system into a brilliant, high-energy beacon. In the Triangulum Galaxy, one such system stands out not for its brightness, but for its bizarre sense of time. Its orbital period, the time it takes for the two objects to complete one full dance around their common center of mass, is strange. It might be extraordinarily long, taking months or even years, which is unusual for such an intense, mass-transferring pair. Or perhaps it is shockingly short, mere hours, implying the stars are practically touching. Even more puzzling, the period might not be constant at all, but changing erratically, speeding up and slowing down in a way that defies simple gravitational mechanics. This unusual periodicity is a direct window into the complex physics of the system. First, it reveals the nature of the donor star. A very long orbital period suggests the donor is a giant star with a vast, extended atmosphere. The compact object orbits far out, but still skims the tenuous outer layers of the giant, pulling in a slow but steady stream of gas. A very short period, on the other hand, points to a dwarf star in an incredibly tight orbit, its entire being stretched and distorted by its partner's gravity, feeding a torrent of material. The erratic changes in period are the most telling clue. They point to a dynamic, messy relationship. One major cause could be the donor star itself. Many stars like this pulsate or have strong stellar winds. If the rate at which it loses mass fluctuates, the entire balance of the binary system shifts. As mass is transferred from one star to the other, the center of gravity between them moves, subtly altering the orbital dynamics and causing the period to change. It is like two ice skaters holding hands and spinning. If one skater suddenly pulls their arms in, the spin changes dramatically. Another factor is the accretion disk itself. This swirling maelstrom of hot gas is not a simple, passive ring. It can develop instabilities, becoming warped or developing dense clumps that create a drag on the orbiting stars. Magnetic fields, especially from a neutron star, can also interact chaotically with the disk, applying brakes or accelerations that tweak the orbital timing. Observing this system is an exercise in extreme patience and precision. Astronomers must monitor its X-ray output over years, building a light curve that captures every eclipse as one star passes behind the other, and every subtle shift in brightness caused by the wobbling, precessing accretion disk. They are essentially listening to the heartbeat of a cosmic vampire and finding that heartbeat is irregular. By decoding this irregular rhythm, they learn not just about the end states of stars, but about the fluid, turbulent processes that govern matter under the most extreme conditions gravity can provide. This strange object is a natural laboratory for fundamental physics, its unusual clock ticking to the rhythm of gravity, magnetism, and plasma in a violent, intimate dance. The erratic heartbeat of that binary system is a whisper compared to the final, thunderous blast of a supernova. Within the Triangulum Galaxy, astronomers have turned detective, sifting through the aftermath of a stellar explosion to find the culprit. They are searching for the progenitor star, the one that existed before the cataclysm, and what they have found or failed to find rewrites the final act of a star's life. When a massive star explodes, it leaves behind a glowing remnant and often a dense core like a neutron star. By comparing modern, high-resolution images of the explosion site with archival photographs taken before the blast, scientists can literally pinpoint which star is missing from the sky. It is a cosmic game of spot the difference on an unimaginable scale. In some cases within M33, this search has been successful, but the result is startling. The star that vanished was not a swollen, cool red supergiant, as traditional models often predict for certain types of supernova. It was a hot blue supergiant. This is a profound challenge to stellar evolution theory. A blue supergiant is a massive star in a relatively earlier, more compact phase of its life. For it to explode suggests it skipped the expected red giant phase entirely, or passed through it with astonishing speed. The leading explanation is that the star lost enormous amounts of mass through fierce stellar winds or through interaction with a companion star, stripping away its outer hydrogen layers prematurely. This exposed its hotter, helium-burning core, making it appear blue. When its core finally collapsed, the explosion looked different from a standard supernova, potentially lacking certain chemical signatures because the star had already shed so much of its atmosphere. It died young and blue, not old and red. In other cases, the search yields nothing. The archival images show no bright star at the precise location of the supernova. This missing progenitor is a deeper, more unsettling mystery. It implies the star that exploded was intrinsically faint before its death, too dim to be seen in the pre-explosion photographs. This points to a star that was already deeply shrouded, perhaps having ejected a massive, opaque cocoon of gas and dust in the centuries before its demise. In this scenario, the star was literally hiding in plain sight, invisible behind its own funeral shroud until the supernova blast ripped through it. Alternatively, it could mean the progenitor was a very low-mass star in a binary system that was somehow pushed to explode, a scenario that stretches our understanding of supernova triggers. Whether found as a surprising blue giant or missing entirely, each progenitor tells a story of a star's final, secret years. The light we see from the supernova itself is just the final flashbulb. The progenitor is the photograph of the star in the years leading up to it. By finding and classifying these stars, astronomers are reading the final chapters of stellar biographies, discovering that the path to a violent end is far more varied and dramatic than our textbooks once suggested. Every identified progenitor, especially the unexpected blue ones, is a crucial data point, forcing us to revise the complex equations that describe how the most massive stars live and die. The final, violent biography of a supernova is written in a single flash, but some stars choose a slower, more complex path to their end. In the Triangulum Galaxy, a strange binary system offers a living preview of this drawn-out cosmic drama. This is a symbiotic star, a pairing so intimate and chemically complex it acts as a single, erratic organism. the system consists of two stars in a slow, vast orbit. One is a cool, bloated red giant, a star in its late stages, gently puffing its atmosphere out into space in a steady stellar wind. Its partner is the ghost of a star that has already died, a white dwarf. This Earth-sized remnant is incredibly dense and hot, a smoldering ember of stellar core left behind. These two could not be more different, yet they are bound together in a delicate, destructive dance. The white dwarf does not simply orbit the red giant, it feeds on it. As the red giant's wind streams outward, the white dwarf's fierce gravity captures a portion of that gas, pulling it into a swirling accretion disk around itself. This stolen material, rich in hydrogen, eventually rains down onto the white dwarf's searing surface. For a time, this hydrogen accumulates in a layer on the dense star. Then, when the pressure and temperature at the base of that layer become too great, it ignites in a runaway thermonuclear explosion. This is not a supernova that destroys the star, but a smaller, repeating nova-like outburst. The system suddenly flares in brightness, sometimes by a factor of 100 or more, for weeks or months before settling back into its quiet state. This cycle of gentle feeding and violent ignition can repeat for thousands of years. What makes this object truly strange, however, is the shared environment they create. The combined radiation from the hot white dwarf and the outbursts, along with the red giant's cool light, illuminates and excites the gas flowing between them. This creates a unique composite nebula that envelops the entire binary system. When astronomers point their spectrographs at this object, they see a bewildering mix of emission lines. They detect the familiar fingerprints of hydrogen and helium, but also lines from highly ionized atoms of oxygen, nitrogen, and neon, signatures of the white dwarf's intense ultraviolet radiation. At the same time, they see the absorption bands of molecules like titanium oxide, a hallmark of the red giant's cool atmosphere. It is as if the spectrum of a hot nebula and a cool star were printed on top of each other. This bizarre combination is the definitive signature of a symbiotic star, a celestial chimera. Studying this system is like having a front-row seat to the late stages of stellar evolution, but with the process dramatically accelerated and externalized. We see mass transfer in action, the same process that can lead to cataclysmic variables and possibly even certain types of supernova. We observe the chemical enrichment of space as the outbursts and winds from both stars spray newly forged elements into their shared nebula. Each component, the donor, the accretor, and the glowing gas interacts continuously, offering a dynamic model of how binary stars evolve together. This strange object is not just a star, it is an ongoing experiment in astrophysics, demonstrating how the death of one star can radically alter the life and the eventual death of another. That delicate dance of two stars unfolds within a galaxy itself shaped by an invisible hand. The Triangulum Galaxy, like all spirals, is held together by a force we cannot see, dark matter. The first clue to its hidden architecture comes from its graceful spin, a motion that betrays a profound secret. When astronomers measure how fast stars and gas orbit the galaxy's center at different distances, they plot a rotation curve. According to the laws of gravity and the visible mass of stars and gas, we would expect speeds to drop off sharply as you move outward, like planets in our solar system where distant Pluto crawls compared to speedy Mercury. But in M33, and indeed in all spiral galaxies, the rotation curve stays flat. Stars and gas far out in the galactic suburbs orbit just as fast as those near the core. This can only mean one thing: the galaxy is embedded in a vast spherical halo of invisible mass dark matter, whose gravitational pull keeps those outer stars whirling at unexpected speeds. The precise shape of M33's rotation curve allows scientists to map the density profile of its dark matter halo, estimating how this mysterious substance is distributed from the core to the far outskirts. The puzzle is that M33's halo appears less massive and more concentrated than standard cosmological models predict for a galaxy of its size and type. It seems to have less dark matter than expected, or perhaps its dark matter is packed more tightly toward the center. This anomaly leads to the second line of evidence, which comes from the galaxy's entourage. In the prevailing model of the universe, dark matter halos are not smooth. They are lumpy, with smaller subhalos that should host dwarf satellite galaxies. The Milky Way has dozens of such satellites. The Triangulum Galaxy, however, appears to have very few confirmed companions. This scant satellite count could be a direct result of its seemingly lighter dark matter halo, a smaller gravitational well that captured fewer dwarf galaxies over cosmic time. Alternatively, it might mean its satellites are incredibly faint and difficult to detect, lost in the glare of the magnificent spiral itself. There is also the subtle test of gravitational lensing, where the galaxy's mass bends light from distant background objects. While strong lensing is rare for a galaxy as close as M33, careful studies of weak lensing effects could, in principle, weigh its total dark matter content independently. Any discrepancy between this weight and the weight suggested by its rotation would point to an even deeper mystery. So, is the Triangulum Galaxy's dark matter normal? The evidence suggests it is an outlier, a galaxy that either formed in an unusually quiet environment, avoiding major mergers that would have piled on more dark matter, or one whose visible stars formed with astonishing efficiency, making it appear brighter relative to its dark foundation. This duo of anomalies, the rotation curve and the missing satellites, paints a picture of a galaxy that is not just a collection of strange visible objects, but one whose very invisible skeleton has a unique and puzzling shape. Yet the gravitational pull of dark matter cannot hold every star captive. Beyond the faint outskirts of the Triangulum Galaxy, astronomers are tracking points of light that seem to belong to no galaxy at all. These are intergalactic star candidates, lonely suns adrift in the immense, empty gulf between M33 and its colossal neighbor, the Andromeda Galaxy. They are cosmic orphans, and their very existence tells a story of galactic violence on a grand scale. The evidence for these stars is both simple and haunting. In deep, wide-field surveys of the region between the two galaxies, telescopes pick up the faint glow of individual stars. By carefully measuring their apparent brightness and color and comparing that to models of stellar evolution, astronomers can estimate their distance. The results are startling. These stars are too far away to be part of the Milky Way's halo, yet not associated with any known dwarf galaxy or visible stream of the Triangulum or Andromeda. They appear to be truly isolated, suspended in the intergalactic void. How did they get there? The leading theory is one of immense force. During close encounters or mergers between galaxies, the chaotic gravitational forces can act like a slingshot, flinging individual stars out of their galactic homes at tremendous speeds. These stars become hypervelocity runaways, moving so fast they can completely escape their galaxy's gravitational pull. Over millions of years, they travel far into the emptiness between galaxies. Another possibility is that they are the last survivors of tiny dwarf galaxies that were completely torn apart and digested by a larger galaxy like Andromeda, their stars scattered into the void like dust from a shattered vessel. Confirming their isolation is one of astronomy's most delicate challenges. The greatest difficulty is proving they are not simply part of an ultra-faint, undiscovered stream of debris, a filament of stars too thin for our current telescopes to see as a connected structure. To confirm an intergalactic star, astronomers must rule out every other possibility. They search for any hint of clustering with other stars at the same distance. They look for subtle motions, a proper motion, that might show it is moving on a trajectory clearly unbound from any known galactic structure. They analyze its spectrum to determine its metallicity, the abundance of heavy elements. A star born in the crowded disk of a spiral galaxy would have a different chemical signature than one born in a small, primitive dwarf galaxy. Each piece of data helps build the case for its solitary origin. The poignant image of these isolated stars is a powerful one. They are not part of a glittering spiral arm or a dense cluster. They shine alone, their light traveling for millions of years across a darkness so vast it is difficult to comprehend. If you stood on a hypothetical planet orbiting such a star, the night sky would be almost empty. Your host galaxy would be a distant, receding smudge of light, and the nearest neighbor stars would be impossibly far away. These cosmic orphans remind us that the grand structures of the universe are not permanent, and that the forces which build galaxies can also cast pieces of them away, forever alone in the dark. While intergalactic orphans wander the void, a far older traveler has been found much closer to home. Orbiting the outskirts of the Triangulum Galaxy is a solitary giant star, a relic so ancient its composition tells a story from the dawn of time. This star, a resident of the galaxy's extended halo, is profoundly metal-poor. In astronomy, metals mean any element heavier than hydrogen and helium. This star has only a tiny fraction of the heavy elements found in our Sun, making it a pristine fossil from the universe's first generations. Its composition is a direct window into the early cosmos. In the beginning, after the Big Bang, the universe contained only hydrogen, helium, and trace lithium. The first stars, known as population 3 stars, formed from this pure primordial gas. They were behemoths living fast and dying young in colossal supernova. Those first explosions forged the first heavy elements, carbon, oxygen, silicon, and iron, and scattered them into space. The next generation of stars, population 2, formed from gas enriched by those first supernova. They contain a small but measurable amount of these metals. The star we see in M33's halo is a classic, extremely metal-poor population 2 star. It is not one of the mythical first stars, but it is a direct descendant, formed from material that was only lightly seasoned by a single prior generation of stellar explosions. Studying its atmosphere through spectroscopy is like reading a chemical biography of the cloud that birthed it billions of years ago. So how did this ancient star end up in the halo of the Triangulum Galaxy? There are 2 compelling origin stories, each revealing a different chapter of galactic history. The first is that it is a true native, one of the very first stars to coalesce within the primordial cloud that would become M33. In this scenario, it formed during the galaxy's initial chaotic collapse, and its orbit has kept it in the sparse outer halo ever since, a founding member that never moved into the crowded downtown of the galactic disk. The second possibility is that it is an immigrant captured from a dwarf galaxy that was torn apart and consumed by the growing Triangulum Galaxy long ago. Small dwarf galaxies often have very low metal content because they form stars slowly and inefficiently. When a large galaxy consumes a dwarf, it strips away the dwarf stars, scattering them into its own halo. This star could be a survivor of such a galactic feast, its low metallicity a badge of its origin in a smaller, more primitive system. This makes the star a crucial piece of evidence in the field of galactic archaeology, where astronomers act as cosmic historians, using the chemical fingerprints and motions of ancient stars to reconstruct a galaxy's formation. By measuring not just its composition but also its precise path through the halo, scientists can trace its lineage. Is it moving in a way consistent with having formed in place, or does its trajectory suggest it was hurled into the halo from a disruptive merger? Each metal-poor giant star like this is a time capsule, a single data point in a vast statistical puzzle. By finding and studying many of them, astronomers can begin to answer fundamental questions. Did the Triangulum Galaxy build its halo mostly from accreted dwarf galaxies, or did its earliest stars form in a great in situ collapse? The extremely low metallicity of this particular star pushes the timeline of its birth back to the galaxy's very earliest days, making it one of the most direct links we have to the Triangulum Galaxy's infancy, a silent witness to the first flashes of light in a newborn spiral. The ancient halo star is a fossil of the galaxy's birth, but another object in the Triangulum is a living engine of relativistic fury. Here, astronomers have identified a candidate for a microquasar, a stellar system that mimics the most violent phenomena in the universe on a miniature scale. At its heart lies a stellar mass black hole or a neutron star, the remnant of a dead sun. What makes this system extraordinary is not just its existence, but its behavior. Instead of quietly accreting material from a companion star, this compact object is powering a pair of high-speed jets, narrow beams of plasma blasted outward at nearly the speed of light. These jets slam into the surrounding interstellar medium, creating visible, lobe-like structures that glow brightly in radio waves, like cosmic headlights illuminating the void ahead. Simultaneously, the hot accretion disk swirling into the black hole emits intense X-rays. This combination, the twin radio lobes and the brilliant X-ray core, is the definitive signature of a microquasar. It is a scaled-down replica of the quasars and active galactic nuclei that blaze at the hearts of distant galaxies, but here, the monster is only a few times the mass of our Sun, and its jets span light-years instead of hundreds of thousands of light-years. This accessibility is what makes the object so valuable. Studying a quasar in a distant galaxy is like trying to understand a hurricane from a satellite image. You see the immense structure, but the fine details of the engine are lost in the glare and the distance. A microquasar, however, is like having that hurricane in a laboratory jar. The entire cycle, from accretion to jet launching to the jet's interaction with its environment, happens on a human timescale. Changes in brightness, fluctuations in the jet's power, and the expansion of the radio lobes can be tracked over months and years, not millennia. This provides an unparalleled testbed for the fundamental physics of relativistic jets. How are particles accelerated to such incredible speeds? What role do magnetic fields play in collimating the jets into such narrow beams? Why do some accreting black holes produce powerful jets while others do not? By observing this candidate in M33, astronomers can watch these processes unfold in real time, applying the lessons learned to understand the giants that shape entire galaxies. This strange object, a miniature cosmic cannon, demonstrates that the universe often repeats its most extreme phenomena at every scale, offering us a manageable window into the most energetic laws of physics. The miniature fury of a microquasar is dwarfed by the impending doom of a single, unstable giant. Among the galaxy's most massive stars, one stands out as a true cosmic powder keg, an unusually luminous blue variable. This star is a behemoth millions of times brighter than our Sun, and it is in a state of perpetual, violent crisis. Stars of this class are the most massive and unstable known, spending their final millennia in a turbulent dance between extreme outbursts and relative calm, constantly threatening to tear themselves apart. The most famous example in our own galaxy is Eta Carinae, which underwent a colossal eruption in the 1840s, briefly becoming the second brightest star in the night sky. The star we observe in the Triangulum Galaxy is a sibling to that monster, a candidate for a similar catastrophic fate. Its defining characteristic is its wild variability. It does not pulse gently, it convulses. Over years or decades, its brightness can change dramatically, not by a few percent, but by factors of 2 or more. These are not simple changes in output, they are physical events. The star's outer layers become so inflated and unstable that radiation pressure from within overcomes gravity, and the star violently ejects massive shells of its own atmosphere into space. Each eruption is a prelude to the final supernova, a rehearsal for the ultimate explosion. The evidence of its violent past is written in the glowing nebula that surrounds it. Just as Eta Carinae is shrouded by the beautiful bipolar homunculus nebula, this star in M33 is likely encased in its own expanding shell of ejected material. This nebula is a fossil record of the star's previous tantrums. By studying its shape, expansion speed, and chemical composition, astronomers can read the history of the star's instability. Is the nebula a smooth, symmetric bubble suggesting a single, giant eruption, or is it clumpy and asymmetric, pointing to multiple directional outbursts? The answers tell us about the mechanics of these catastrophic mass loss events. What drives a star to such extreme behavior? The core of a luminous blue variable is a furious nuclear furnace, fusing elements at a prodigious rate. This generates tremendous outward radiation pressure. In these most massive stars, that pressure nearly balances the inward crush of gravity. The star exists on a knife's edge. Any slight increase in internal energy, perhaps from a fluctuation in the fusion rate, can push the balance over the edge, causing the outer layers to balloon outward and be ejected. The star then collapses back, regains equilibrium, and the cycle begins anew. This precarious state cannot last. Each eruption strips away more of the star's mass, bringing its core closer to exposure. Eventually, the core will run out of fuel. When that happens, the support against gravity vanishes and the core will collapse catastrophically. The result will be one of the most energetic events in the universe, a supernova, or perhaps even a hypernova, accompanied by a long-duration gamma-ray burst. This makes the luminous blue variable a ticking time bomb. We are witnessing the final, most dramatic act of a stellar life, a period of violent instability that directly precedes the grand finale. By monitoring this star, astronomers hope to catch the warning signs of its impending explosion. Will it undergo another great eruption first, or will the next outburst be the supernova itself? This strange object is a cosmic alarm, its flickering light a countdown to an event that will, for a brief moment, outshine its entire host galaxy. The final strange object in the Triangulum Galaxy is a prediction, a future cataclysm written in the orbital decay of two doomed stars. Somewhere within its spiral arms, a tight binary system ticks like a cosmic clock. Its two components, whether massive stellar remnants like neutron stars or black holes, or the massive stars that will become them spiraling inexorably inward. With every orbit, they lose a minuscule amount of energy, radiating it away as ripples in space-time itself. This system is a progenitor, a factory for gravitational waves that have not yet reached us but one day will. It represents the next great chapter in our exploration, where we move from observing light to listening to the very fabric of the universe. For now, this system is a quiet candidate, identified by its telltale characteristics. It might be a pair of massive hot stars whose fierce winds are drawing them together, or it could already be a binary pulsar, two ultra-dense neutron stars emitting precise radio ticks that are gradually speeding up as their dance accelerates. The key is the orbit, a slow, relentless tightening that matches the predictions of Einstein's theory of general relativity. Each completed circuit takes a fraction of a second less than the one before, a decay so small it requires years of patient observation to measure, yet it confirms that energy is leaving the system. That energy is escaping as gravitational waves, stretching and compressing space-time on a journey across the cosmos. The ultimate fate of such a system is a collision of almost unimaginable scale. After millions of years, the two objects will be so close they orbit thousands of times per second. Then, in a final, frenzied moment, they will merge. If they are neutron stars, the collision will forge heavy elements like gold and platinum in a blinding kilonova explosion. If they are black holes, they will simply vanish into a single, more massive hole, their final moments shaking space-time with a thunderous chirp. This event will release more power in gravitational waves than all the light from every star in the observable universe combined at that instant, and for the first time in history, we have the means to hear it. Observatories like LIGO and Virgo are listening for these very signals, the whispers from such distant mergers. The profound promise of this future event lies in multi-messenger astronomy. Imagine the alert, a chirp of gravitational waves detected, pinpointed to a region of sky that includes the Triangulum Galaxy. Telescopes across the planet and in space would immediately swivel, searching for the counterpart flash of light, the gamma-ray burst, or the new glow of freshly forged elements. Witnessing both the space-time ripples and the electromagnetic fireworks from a single event in a known galaxy would be a transformative moment. It would allow us to calibrate the cosmic distance ladder in a new way, probe the extreme states of matter inside neutron stars, and directly test gravity under the most severe conditions. The candidate system in M33 is a promise of that future, a known address for a coming apocalypse. So our journey through 25 strange objects ends not with a conclusion, but with an invitation to listen. The Triangulum Galaxy has shown us quiet hearts and screaming beacons, ancient fossils and newborn cities, invisible scaffolding and orphaned stars. Each oddity is a piece of a larger puzzle, teaching us that the universe is far more varied, dynamic, and inventive than we ever supposed. And now, as we look at its familiar spiral, we can also listen for its future, knowing that one day, its silence will be broken by a ripple that passes through everything, a final, strange message from a galaxy that never ceases to amaze. These 25 strange objects are not scattered curiosities in a cosmic museum. They are characters in a single, interconnected story. The grand cycle of galactic life binds them all together, each one a consequence or a cause of another. Consider the magnificent stellar nursery NGC 604, where thousands of stars are born. That furious birth creates the massive, short-lived stars that are destined to explode as supernova. Those explosions, in turn, leave behind the bizarre remnants with their distorted shapes and the compact objects, the black holes and neutron stars that power the X-ray binaries and the microquasars. The material blasted out by those supernova enriches the surrounding gas with heavy elements, the very metals that will be incorporated into the next generation of stars. This is how the ancient metal-poor halo star connects to the brilliant blue giants being born today. The halo star is a relic from a time before many supernova had seeded the galaxy, while the stars in NGC 604 are built from gas that has been recycled through countless such explosions. The runaway star, flung from a cluster by a supernova or a gravitational slingshot, is a direct product of this violent environment, a piece of shrapnel from the stellar chaos. Even the final, unstable luminous blue variable is a product of this cycle, a massive star born from enriched gas now teetering on the edge of contributing its own explosive elements to the mix. Beneath this visible drama of birth and death lies the invisible architecture of dark matter. The galaxy's unique rotation curve and its scant collection of satellite galaxies hint at a specific distribution of this mysterious substance. This dark matter halo is the gravitational mold into which the galaxy formed. Its pull governs the motions of everything from the vast, starless hydrogen clouds drifting in the outskirts to the tight orbits of binary stars spiraling toward merger. It dictates the overall shape and stability of the galaxy, creating the relatively calm spiral arms where objects like the dark globule can slowly collapse, and the crowded environments where superstar clusters can be born. The strange quiet at the galaxy's core, the missing supermassive black hole, might itself be a result of this particular dark matter distribution and the galaxy's peaceful merger history. Every object, from the smallest variable star to the largest nebula, exists within this delicate balance between the gravity of seen and unseen matter. The ghostly infrared object, the planetary nebula with its twisted shape, the symbiotic star's slow theft, all are local expressions of universal physics playing out within this specific galactic framework. They are not isolated wonders, but threads in a single, magnificent web, each one revealing a different facet of how a galaxy lives, breathes, and evolves across billions of years. But the story of these 25 strange objects is far from finished. Our current view is like a magnificent painting glimpsed through a dusty window, and a new set of tools is poised to wipe the glass clean. The next generation of observatories will not just see more, they will see differently, transforming our puzzles into profound understanding. At the forefront is the James Webb Space Telescope, an instrument designed to see the birth of light itself in the infrared. For the unidentified infrared object, that ghostly heat source, Webb is the ultimate detective. It will peer straight through the dusty veils that hide it, analyzing the precise chemical fingerprints in its glow to answer the fundamental question: is this a hidden stellar nursery, a dying star's shroud, or something else entirely? Its incredible resolution will also dissect the chaotic hearts of superstar clusters and the intricate structures of planetary nebulae, revealing the dynamics within. Meanwhile, back on Earth, the Vera C. Rubin Observatory will conduct a relentless, decade-long movie of the entire sky. This will revolutionize our understanding of change. That erratic variable star, its flickers measured in painstaking detail over years, will have its entire life story documented with unprecedented precision. The Rubin will catch the subtle brightening of stars on the verge of eruption, track the orbital quirks of X-ray binaries in real time, and monitor the slow, fateful brightening of the luminous blue variable, potentially giving us a warning siren before its final, cataclysmic explosion. It will find thousands more variable objects we have not even begun to catalogue, each one a new mystery. And then we have the listeners, the gravitational wave observatories like LIGO, Virgo, and the future space-based LISA. They wait for the thunderclap from that inspiraling binary system, the moment when its two components finally merge. Detecting that signal from a known galaxy like Triangulum would be a watershed, allowing us to marry the ripple in space-time with the flash of light, creating a complete picture of the most violent events in the universe. This multi-messenger future is complemented by a new ear on the radio sky. Advanced arrays like the square-kilometer array will map the faintest hydrogen clouds and the delicate tidal streams of dwarf galaxies with stunning clarity, probing the dark matter distribution like never before. New X-ray observatories will watch the feeding habits of black holes in the X-ray binary and the microquasar with sharper eyes, detailing the physics of accretion at the event horizon. Each new tool offers a new sense with which to perceive the cosmos. We are moving from taking snapshots to directing a continuous, multi-spectral documentary of galactic life. The strange objects of the Triangulum Galaxy are no longer static curiosities. They are dynamic experiments waiting for their next measurement. The puzzles we have outlined are not dead ends, they are invitations, and humanity is building the keys to unlock them. From the silent potential of dark matter to the screaming birth of stellar cities, the Triangulum Galaxy is a living museum of cosmic extremes. Each of these 25 strange objects, from the missing black hole to the ticking binary, is not an isolated wonder. They are interconnected chapters in a single, sprawling biography of a galaxy. The quiet heart influences the frenetic star formation in its arms. The ancient halo star tells the story that the superstar cluster will one day become. The runaway star is a piece of shrapnel from the same violent processes that create the microquasar. Every oddity, every rule breaker and quiet rebel is a vital clue in the grand puzzle of how a galaxy breathes, grows, and ultimately changes across billions of years. They show us that the universe is not a static painting, but a dynamic, ever-evolving story, and our neighbor M33 is one of its most eloquent storytellers. This relentless drive to map its mysteries, to listen for its gravitational whispers and peer through its dusty veils, speaks to something fundamental within us. It is the human desire to look into the night sky and not just see points of light, but to understand our place within the magnificent, interconnected tapestry they weave. So tell me, which of these cosmic oddities captured your imagination the most? Was it the ghostly infrared object, the stellar nursery of impossible scale, or the ancient star from the dawn of time? Let me know your thoughts in the comments below, and if you want to join the search for more deep space mysteries, be sure to subscribe. The universe is stranger than we can suppose, and the next discovery is always just over the